In this circuit, an ammeter is connected in series with the 2 kilo ohms resistance to find the current through that branch. So the ammeter is not an ideal one though. It has an internal resistance of 500 ohms. So we have to find what will be the reading of the ammeter. So basically first we have to find what should be the current through the 2 kilo ohms resistance and so on. Let's see what we'll do. So we are interested in the current through 2 kilo ohms branch. The ammeter is connected there. So the remaining part of the circuit, we can get rid of that by replacing the whole thing using its Thevenin's equivalent. So we just want to get the Thevenin's equivalent of this. So this is the branch and the two terminals, let's call it A and B, and get rid of the remaining one by its Thevenin's equivalent. So let's remove the circuit from, remove the 2 kilo ohms branch and leave it open, and then we can find Thevenin's voltage first. So it's like that, and there's a 60 volts there, 5 kilo ohms, 20 kilo ohms, and here 10 kilo ohms, that's 30 kilo ohms, and 4 milliamps. So these are the, so we have to find what is the voltage here, VAB, if this is AB, which is Thevenin's voltage, the open circuit voltage. So this current will flow only through this loop because it cannot go here because it has no path to come back. So the voltage drop here will be of course 30 times 4, 30 kilo ohms times 4 milliamps will be 120 volts. So that will be the voltage here. So VA is 120 volts. And when we see what is VB here, there is two series resistances connected with the 60 volts voltage source. Here also current will flow only in this direction. So of course the voltage VB will be, if here the VB will be, there won't be any current through 10 kilo ohms resistance. So we have just, this is ground, common ground. So VB will be VB 60 divided by 20 plus 5 times 20. So that will be VB. So 60 divided by 25 times 20. So that's 60 divided by 5 times 4. So 48 volts. So that will be VB. So we can find VAB, which will be this one minus 48 volts. So that will be 72 volts. So that's our VThevenins. So we know which is VThevenins. That's the open circuit voltage. Now we need to find the Thevenin's resistance. So we have to make all the sources inactive. So this there, and this is open now. This is 30 kilo ohms. So this is our A. The current source here, that was here, is gone. This is B, and we have 5 kilo ohms there. We have 20 kilo ohms there, and the voltage source is short circuited, that is 10 kilo ohms. So we have to find what is R Thevenin, which is the resistance seen from RAB, as seen from RAB here. So we can see that 30 plus 10, these two are coming in series, and then these two are in parallel, 20 and 5. 20 parallel 5 will be 20 times 5 divided by 20 plus 5. So that will be 100 divided by 25, which is 4. So we have 30, 10 and 4. These three are in series. So 30 plus 10 plus 4. 4 is the parallel equivalent of these two. So that is 44 ohms, kilo ohms. So that's our Thevenin's resistance. So we have now the circuit like this, 72 volts, 44 kilo ohms, and here is our resistance. So which is 2 kilo ohms. Now I am connecting the resistance, and I have an ammeter which also has an internal resistance. Let's draw it like that, of 0.5 kilo ohms. So it's a pretty high one actually. So this high, this kind of, I mean, an ammeter with this kind of this range of internal resistance is not suitable to measure current measure current through a this low resistance, because this is pretty comparable, just 1/4. If the resistance was say 50 kilo ohms, then the current would be quite close. So anyway, the current here now will be, which is, let's call I2. which will be the current through that. The ammeter reading basically will be 72 divided by 44 plus this will be 2.5. So that will be the, so let's do it like that. The voltage drop across the 2 kilo ohms resistance. So I will do it as the ammeter would measure. So voltage across the 2 kilo ohms resistance will be V2, 72 divided by 44 plus 2 times 2. So that will be the voltage. So that will be 3.13 volts. So that will be the voltage across 2 kilo ohms. Now the real current will be, the current in this case will be, or let's say the real current will be, of course, 3.13 divided by 2, because that's the resistance. If the ammeter had an internal resistance of 0, the ammeter reading would be like this. But since the ammeter has an internal resistance of 0.5 ohms, 0.5 kilo ohms, the current will be 2 plus 0.5. So 3.13 divided by 2 plus 0.5. So that will be the current. So this is 1.56 milliamps, which is the real current, but this will be 1.25 milliamps. Now we can see with the same ammeter, which has the same internal resistance, if the resistance through which the current was supposed to be calculated was like very high, let's say 50 kilo ohms, then the error would be much less, the percentage of error. I'm not doing it, but that's obvious. So this is quite an error, 1.56, but this one is 1.25. So this is the result of the ammeter. This will be the ammeter reading basically.